welcome back to Manish Kumar channel. So today we are going to discuss about the construction of basis for real vector spaces. Okay. So the basic idea of the definition of basis. Basis means V is given set, right? And a subset B is called as basis having element V1, V2 and so on Vn, right? Collection of some elements from V is known as basis if B has two properties. B is linearly independent and the vectors span V. This means the vectors V1, V2, V3 and Vn is going to span the given vector space. Span means any vector can be written as the linear combination of these vectors. Okay. So if these two criteria are going to be qualified for any subset of the V, we can call it as basis for that given vector space. And the number of elements presented in the basis is known as the dimension of the vector space, which we have already seen in the previous video. Okay. So now today we are going to discuss about how to construct the basis. Okay. So there are two methods here, simplified span method and independent test method, right? So these two method is an elegant methods which provide for any set to become a basis. Okay. So what is simplified span method? In simplified span method, the vectors in S becomes the rows of a given matrix A. Okay. So it means any vector in the given set S, we can allot them as a row wise, right? And form a matrix A. And then we solve RREF for that matrix, right? Okay. And for independent test method, what we have to do, the vectors in S becomes the column of the matrix A. So this is the difference between simplified span method and independent test method. So in independent test method, the vectors are arranged in the column wise. Okay. And the same procedure will be followed, like RREF is being performed like reduced row echelon form. Then the basis, the basis created is not a subset of the spanning set yes, but contains the vectors with a simpler form. Okay. It means the simplified span method will produce a basis that are not the element from S actually, right? It will be a very simpler form. But in independent test method, the basis created is a subset of the spanning set S, right? So we will see with an example to understand this difference. Okay. And how do we choose the basis? So the non-zero rows of RREF of the given matrix, we can collect them and we can declare as those vectors are basis vectors. And here the pivot columns, right? Wherever the pivot column you are having, collect those vectors. They are linearly independent actually, and which will be a subset of you know S or even S also, right? So it depends upon the given set is basis or spanning set, right? So you are going to throw out some independent dependent vectors from the S. This is the idea. And here you are going to check the vectors whatever we are going to receive as a rows, right? Non-zero rows of RREF, and this is not the member of S, right? So this is the difference. So let us do one by one. So finding a basis using simplified span method. So let us do this problem. Adopt the simplified span method to find the basis for the subspace of P3 spanned by. So this is the S and the vectors are the polynomials, right? Okay, so we have three polynomials. Okay, so now the P3 P3 is how many bases you require. Basically, you require P3 P3 dimension of P3, Dimension of P3 is 3 plus 1, so 4. So definitely this set, yes, consisting of 1, 2 and 3. There are three members, three vectors in S, then three vectors cannot generate the P3 as whole, right? So they can generate as a subset. So we want subspace. So we want the this S will generate a subspace, right? And what type of subspace are going to be generated? We are going to figure it out, right? If all vectors in this are linearly independent, right? Then this will generate the polynomial P2 because three vectors are required to generate P2. Okay. If any one of them are the linear combination of them, then we are going to throw out, right? So that is the way simplified method works. Okay. So now if you see here, representing these polynomial as a vectors. So I'm going to just express the polynomial in terms of the basis vector like this: coefficient, highest coefficient, row wise. If you see in the spanning method, go to the row wise, allot the vectors, right, as becomes rows of the matrix. So if you see the higher degree 3, 2, x 1. So if I want to write this x3 coefficient is 1 and x2 coefficient is 3, 0 times of x plus 1. So I am going to write 1 minus 3, 0 and 1 as one vector. And I'm going to allocate this vector as row of the given matrix. So it will go in R1 place, this vector. Similarly, this vector will go to R2 and so on, right? This is a simplified span method. We allocate vectors in row wise. And if we want to do simplify independent test method, then we have to assign this vector as column. So we have to take transpose of this vector, right? Row becomes column. Okay, anyway. So let us prepare the matrix A, right? And you know how to apply RREF, right? If you go to a previous video, first video, second video, and third video, you will know difference between RREF, REF, and how to apply RREF. So I request to refer my previous video, right? Okay, so once you perform RREF on 8, you will get the only this non-zero rows, this non-zero rows, and this non-zero rows, right? So you got all three non-zero rows, okay, for this space. So when you extract this, what will happen to it? This, this, and this. So it is a very simplest form. If you see simplest form, then the given S which you have received before. If you see yes looks like the original vectors, right? Of sitting in P3. But now after simplified span method, the basis which you have constructed consisting of three elements, right? And this forms the basis for subspace spanned by S. Okay. So this is the basis we are going to get, and which is not the members of S. That is what the simplified span method basis is. Okay. So now next, finding the basis from a spanning set by inspection method. There is another method. You can just look by inspection. Okay, this can be the element to be in the basis. So you can do that way also. Okay, so let S be a finite subset of vector space. So let S be a finite set of vectors spanning a vector space V, right? So base step, what you have to do, choose any non-zero vector T1 in S and repeat the following steps as many as possible. What is the step? Assume T1, T2, and so on, Tk minus 1 have already been chosen from S, right? And suppose if you got any Tk at any stage K, this belongs to S, right? such that tk does not belong to span of this. It means that tk does not belong to span means tk cannot be written as the linear combination of alpha 1 t1 plus and so on alpha k minus 1 tk minus 1. So this cannot be written as the linear combination of tk cannot be written as the linear combination of the elements of this set S consisting of t1 t2 tk minus 1. It means that if this is not possible, then tk is independent, right? Independent independent of t1 t2 tk minus 1. Okay, and then you can bring into the original set yes and then repeat that process. Okay, so the final set constructed is a basis. Okay, so let us do very good example here. So consider yes is consisting of two vectors, right, in R3. Since yes does not span R3, right, I want to generate R3 using this set. Okay, so by inspection method we can take non-zero vector. This is non-zero actually, right? Non-zero vector such that this does not belong to span of given yes, right? So it is clearly seem that you can see very clearly that this vector can never be written as the linear combination of these two. You see the third tuple is 1, non-zero, right? So no matter if you want to say 0 1 0 0 1 can be a combination of alpha times of 1 comma 0 comma 0 plus beta times of 0 comma 1 comma 0, then what exactly had happened, whatever alpha and beta you choose, no matter whether 0 or non-zero, you are not able to generate the last tuple as non-zero because I want non-zero tuple at the last. But here both are zero. So these vectors are not enough to generate the third tuple of these vectors. It means that this will not be possible. It means that this vector is not in span, this criteria. It means that this vector can be added in your yes. So now the final basis will be your including this vector, right? Yes consists of 1 0 0 0 1 0 and 0 0 1. So this is now is our basis, right? And that will generate the entire R3, right? And they all are Li and they can span entire R3, okay, by inspection method. So there is one theorem. Let T be a linearly independent subset of a finite dimensional vector space V. Then V has a basis such that T can contained in B, right? So there is a very good picture, I can say basis, right? And basis means you can say that less than or equal to less than or equal to. Here you can say that span set, and here you can say that Li set, right? So this is a very good relation if you see. If I increase this spanning set, right? So maximal, and if I take minimal minimal to this set, then I will reach towards basis, right? And maximal means I'm going to enlarge this to reach basis, right? So for example, if you see very simple example R3 means dimension of this vector space is 3, dimension of this vector space over uh, R is 3. So basis consists of 3 element, right? So if you see the previous example, 1 0 0 0 1 0 was given as your yes. So they are definitely Li, right? This set is Li. Okay, this set is going to be your Li, but this is Li set, right? But this cannot be the basis because this set has dimension 2. So this set can generate only subspace of R3. So this set has two linearly independent set. It cannot span entire R3 because it can span only planes, right? Planes passing through origin. Okay. But if I add one more vector as I inspection I did and got one more vector 0, 0, 1. So I'm going to increase the size of this set and to reach maximal, right? So I'm going to add this vector as well in this. So I'm going to get the exactly the basis. Now, if you add any more vector, suppose in this set only, Li set, then what had happened? It will be a copy of others. So this set is no longer Li, right? But I want Li. But if you go to maximum, you can only reach to the dimension only, three vectors. You cannot add more than that. In a similar fashion, if you say like 1 0 0 0 1 0 and 0 0 1 and let's say 2 0 0, right? So this set has four vectors, right? So this will definitely span R3, but they are not Li. If you see the relation of these two vectors, this is just the two times of the previous vector, right? So they are not Li. Okay. So if could it be possible to reduce the size of set to throw out some vector from this set to get basis? Answer is yes. If we throw out this vector, still this will span R3, right? These three vectors span R3, and then now minimal spanning set, minimal which span the entire R3 will be going to be the basis. So you are going to get to the basis 3, right? So these number can be higher than basis, these number can be lower than basis, but to have basis, they can reach maximal linearly independent set and minimal spanning set is going to become a basis. This is the result which we can see. So now if you see T is a linearly independent set, then definitely this criteria is going to be hold. If B is a basis and T is Li, so cardinal T, like T set contained in B, right? So T becomes B when this is maximal, right? So this is a subset. Subset means the number of element in T, number of element in B. So T contains in B, right? So now let us see the one more problem. So method for finding basis by enlarging linearly independent subset method, right? So that is called enlarging method. So method for finding basis by enlarging a linearly independent subset. Okay, so enlarging method. What is the idea here? Let T be T1, T2, T3, which is given as Li, a subset of finite dimensional vector space V. Then find a finite spanning set A, A1, A2, and so on, An for V. Form an ordered spanning set S by adding these many vectors to V and use either of the method, independent test method or inspection method, to produce a subset B of S, right? So how does it work? And then B is called as basis of V containing T. Okay, so now let us do one problem. Enlarge the given linearly independent subset T of a vector space M3 cross 2 to a basis B, okay, that contains T. So T together with some more is going to become the basis of M23, right? So how many vectors are here? 1, 2, 3, 4, 4 vectors, right? And what is the dimension of T4 M23 M32? Dimension will be M into N, right? So for Mn is equal to M into N, so M equal to 3 and N equal to 2. So 2 into 3, 6. So 6 vectors are required to span entire vector space, but T contains only 4. Matrices means the vector will looks like a matrix actually. Okay. So we need to add two more to reach towards basis, right? In the previous step, if you see, okay. So now what you have to do? So finding additional basis matrices. So given set T consists of four matrices which are already linearly independent. So we need to find two more matrices to get the basis for M32. What we will do exactly here, we will uh, keep vectors as column wise for the given matrix, right? So how we have, you can choose whatever the way you want, but what I have followed, I have taken these 3 minus 1 0, then appended this one 0 5 1, but keep the same order for all the vectors, okay. So now if you see, I have added in the same way this one one column, similarly second column, third column, fourth column, okay. Now since I know the basis consists of six, uh, because the basis consists of six element, right? So now I am adding standard basis, right? And since this standard basis is already going to give the confirmation of spanning this entire vector space, but we want the basis consisting of these vectors as well. So this is the method. We are going to add the standard basis and apply RREF on it, right? So after applying RREF, what we got, this is the pivot, this is the pivot, this is the pivot, and this is the pivot, because they all are Li and no pivot in this column, right? You got my point or not? Then you have to switch down and then get this and then get this, right? So these two vectors are going to become the pivot for this matrix, okay? So now 4, 5 and 6, and then now I find the pivot here and then pivot here. So only these two vectors I am going to call, and how I will take this first column of the matrix 0 0 0, and then these three 0 1 0 will be one of the my new vector which is added to T, and then 0 0 0 and then 0 0 1. So these two vectors I'm extracting from this matrix and adding with together with your T. So the final basis will be this 4 vector and this. So you can do a similar problem with different vector space as well. The idea is to incorporate all the standard basis and then apply RREF and then see how many pivot elements on your standard basis are. Then keep those into the along with set T. So you can say that this is the basis generated by T. Thank you.